All right. In this module, we're going to start on a new chapter on imperfections in solids. So we've just finished a quite extensive set of lectures, set of modules on crystallography and structures, and most of that had to do with what we would call perfect crystals. And so now we're going to look at what happens when those crystals are no longer perfect, because real crystals are always imperfect and have imperfections. All right, so let's look at these types of imperfections. And first of all, let's look at why we study imperfections. So you might think they're not important and so forth, but they actually are responsible for a lot of different types of properties that we see. The next chapter that we're going to discuss is going to be on atomic motion, so looking at atoms moving around in a solid. So these imperfections are very important for that. And then we're also going to look at a phenomenon in deformation called plastic deformation. So this will be related to mechanical properties of materials. Then a certain type of imperfections key in this aspect. Plastic deformation basically means permanent. So if we deform something into a shape, that is plastic deformation. Catalysis, that is useful for reducing toxic gases and speeding up reactions. This occurs on other types of imperfections and requires them for catalysis to work. And also failure. We're going to talk about failure in this semester as well. And processing flaws and imperfections can result in those failures. So we want to know about imperfections for these reasons, but also others. All right, so let's sort of review, let's go back and look at a perfect crystal. So again, we just talked about structures, and so a perfect crystal we're going to define as something, with a crystalline structure that has all of its atoms in the correct sites as we define in our crystal structures, and then there's nothing extra as well. So everything's located at the site it's supposed to be, and we have nothing extra, nothing missing. And so that's important to keep in mind. And also, the last part of this for a perfect crystal is that this crystal would extend out indefinitely, infinitely, right? And so obviously this cannot occur. So these things are not possible for the most part. And so in that case, we're going to have imperfect crystals. So knowing that we're going to have these imperfect crystals, what we do is we define and classify the different imperfections that we can observe based on their dimension. And so what I mean by that is we can talk about three-dimensional, two-dimensional, one-dimensional, zero-dimensional. So zero-dimensional, when we think of zero-dimensional, we're talking about a specific point. So there's an imperfection at a specific point in the lattice. And so these types of defects are vacancies, interstitial atoms, substitutional. And so we're going to talk about those types. Here's an example real quick, but we're going to go more into detail on those. Next, we have one-dimensional. So 1D, you're thinking about a line. So these are line defects. And the line defects are just another word for dislocations. And dislocations are key for plastic deformation that we talked about. And so we're not going to talk as much about that in this chapter, but we will in later chapters when we talk about plastic deformation. Two-dimensional, this is where we start getting into an area or a plane, right? And so these are the grain boundaries that we mentioned briefly when we talked about polycrystalline materials, and also free surfaces, right? Since a crystal has to be infinitely extending out, any type of surface therefore is considered an imperfection. And so a surface has dangling bonds and so forth, and so that would be considered an imperfection. And since it's an area, we call it a two-dimensional. And then the last three-dimensional, these are volume defects. And so these get to the more processing defects. So we have things like voids in materials where these black what look like particles. They can either be other phases, they can be just pores, empty space, but they're a volume of material that is imperfect to that crystal. So all of these, again, are just defined by the dimensionality of the different types of imperfections. And so what we're going to do now is move on and just talk about point defects to start with, and then we'll move on and talk about the others briefly. But point defects, like you see here, cover vacancies, interstitial atoms, and substitutional. So let's talk about what a vacancy is. So this one's, from its name, is fairly evident what this is, right? We have a structure where everything is where it should be, but a vacancy is something missing that would normally be occupied in that lattice site. So this is a two-dimensional model of a simple structure, and we see that we have atoms next to each other and on top of each other, but here in this spot right here, there's nothing, there's no atom, and you actually see that the atoms around it are kind of deformed into that spot. And so there's actually distortion because there's a vacancy or an empty site in this lattice. So this is a vacancy. So this can occur at atomic sites in metals and so forth, but it can also happen in ionic materials as well, where we're talking about ceramics and so forth. So we don't have to just limit it to atoms. It could be ions as well. And so this causes a distortion, and this type of distortion is actually a tensile distortion based on the lack of that atom here that causes a tensile stress in this vicinity. So that has an effect on the area around the vacancy. All right, so the opposite of that then would be having an extra atom or ion in a normally unoccupied site. So we talked about those interstitial sites in a structure, right? If you look over here, there's an empty site between these four atoms. That's an interstitial. So if we place an extra atom, so if this is a material like copper or iron or some metal that is just composed of one element, if we have an extra atom, we call that a self-interstitial. So if it's just the same material placed in an interstitial, that's a self-interstitial. There's also other types of interstitials that you can add in, right? So if this is iron, and then we place into this interstitial instead of iron, if we place in another atom, say carbon, that's actually what makes steel, and that makes an alloy. So it doesn't have to just be a self-interstitial, but that's one case that we can have. So, and again, we talk about atoms, but it could also be ions as well in these structures. And if you think about the structure here, this is, for example, iron. Well, iron is in this structure, and then the empty spots. Well, if that empty spot was big enough for an iron structure or an iron atom, the structure would probably be different, right? So all of these interstitial sites are actually quite a bit smaller than the atoms. So if we place an extra atom into that structure in a spot not normally occupied, that's again going to cause distortion. And so you can kind of see that all of the atoms around it are pushed out. And so that pushing out is an example of a compressive distortion on the lattice, the opposite of the vacancy. So you can always kind of remember it that way. This is compressing everything around it because we're putting extra stuff into this lattice. So far we've talked about vacancies at specific points and interstitials at certain points, and therefore we have different point defects. So in the next section, we're going to talk about why this occurs and what it means for the overall number of these vacancies or interstitials that we see.